In this lecture, we will discuss about fundamentals of high speed flows. You may recall that we already discussed earlier that when we discuss about high speed flows, thermodynamics becomes a very important issue, and therefore, we are beginning by discussing about some basics of thermodynamics. Let us first look at a perfect gas, and we may recall having discussed that it is a gas in which intermolecular forces are neglected. So, though the molecules are tightly packed in the gas, they are still far enough apart, so that the intermolecular forces are not going to play a major role. So, the equation of state for a perfect gas in such a situation can be given by different forms. We have stated two forms over here. So, the first form is P capital V is equal to bold R into T. So, this is the nomenclature we are following here. So, where capital V is molar volume, its unit is meter cube per kg mole, and capital R is the universal gas constant, which is given by the value 8314 joule per kg mole Kelvin, and which is incidentally the same for all gases, that is why universal. You can write the equation of state for a perfect gas in an alternative manner, like we have shown in the next line. P times small v is equal to unbold capital R into T, where the small v stands for specific volume, which is also representable in terms of density. It is the reciprocal of density, and therefore, its unit is meter cube per kg. Capital R is specific gas constant, and its value is going to change from one gas to the other. Incidentally, for air it is 287 joule per kg Kelvin. So, these values are important ones, you should keep them in mind. What is the connection between the bold R and the unbold R? The connection comes through the molecular weight of the gas. So, when you divide the universal gas constant by the molecular weight of the gas which you are discussing or which you are handling, then you get the specific gas constant for that particular gas. When you look at the gas from a microscopic point of view, it is basically a collection of particles which are in a state of random motion. And if you look at each one of those particles, they have their individual kinetic energy, and when you sum up the kinetic energy, they contribute to the overall energy level of the gas. When you are talking about individual atoms, it is slightly simpler, but when it is a collection of molecules, a collection of atoms which forms molecules of the gas, then you are talking about also the rotational and the vibrational motions of the atoms within the molecule, which would contribute to the energy of the gas. And of course, if you go into each one of the constituent atoms, then the electrons are in a state of continuous motion, and then they also add on to the energy. Therefore, when you account for all these energies and you sum them over all the particles that comprise the gas, you end up getting the so called internal energy of the gas, which is often expressed in specific terms, that means per unit mass terms, and represented by small e. The system comprises of gas particles which are in a state of equilibrium when these particles are in a maximum state of random motion. So, that is the microscopic viewpoint. When you look at it from a macroscopic point of view, you look at the gas in the form of a continuum. So, you lose the discreteness aspect of the gas and look at it as though it is a continuous medium, and in such a situation equilibrium would exist when there are no gradients of the velocity, pressure, temperature chemical concentrations through the system. So, under equilibrium, the system would demonstrate uniform properties, and for equilibrium system of a real gas where intermolecular forces are important, and also for an equilibrium chemically reacting mixture of perfect gases, the internal energy is a function of both temperature and volume. It is true even for another important thermodynamic property, enthalpy, which when stated in specific terms, that means specific enthalpy, which is enthalpy per unit mass, is the sum of the internal energy and the product of pressure times specific volume. So, we have represented that fact in the last line here as E being a function of T and V, and so is H, both for a real gas and a chemically reacting mixture of perfect gases. If the gas is not chemically reacting, and if we ignore the intermolecular forces, the resulting system is a thermally perfect gas. So, we are taking out chemical reactions and we are taking out intermolecular forces, that means effects of these two, and then you have a thermally perfect gas. So, in such a situation, if you are looking at internal energy and enthalpy, they would become functions of temperature alone. And when you look at the specific heats at constant volume and pressure, that means Cv and Cp respectively, they also become functions of temperature. So, the dependence on specific volume goes away, it is only a function of temperature now. Now, if the specific heats are constant, then the system happens to be a calorically perfect gas. That means, they do not have any dependence on temperature either, they become constants. In that situation, you have a calorically perfect gas. When does such a gas behavior come up? So, we will find that in many compressible flow problems and applications, pressures and temperatures are moderate, not extremely high, not extremely low. It is true for both pressure and temperature, and then the gas can be considered as calorically perfect. In such a situation, internal energy and enthalpy in specific terms will be representable using these formulae, which basically means that at absolute 0, both these quantities will also limit to 0. Further, for a calorically perfect or a thermally perfect gas, we have the following relations. They are not valid for either a chemically reacting or a real gas. So, the following relations hold good not only for calorically perfect gas, but also for a thermally perfect gas. So, what are the relations? When you take a difference between Cp and Cv, you get the gas constant, the specific gas constant. And in this expression, the Cp, how do you obtain it? If you take a partial derivative of enthalpy with respect to temperature at constant pressure, you get Cp. When do you get Cv, specific heat at constant volume? You get it when you are taking a partial derivative of the internal energy with respect to temperature at constant volume. So, this is at constant pressure, this is at constant volume, and therefore, they figure here in the respective specific heats, and you need to recall that the partial derivatives are both taken in terms of time derivatives of either enthalpy or internal energy. So, it is enthalpy in the case of Cp and internal energy in the case of Cv. Now, if you divide this equation by Cp, this is what you get, and the ratio Cp by Cv gives you gamma, that is the specific heat ratio. Please do not confuse this Cp with coefficient of pressure. because we have discussed with it at length. Here it has a very different context. So, here we come back to this equation, you have a ratio C V by C P. So, that is basically 1 by gamma, and from this equation now you can solve for C P and it comes out to be this, it is gamma r by gamma minus 1. Similarly, you can solve for C V and you come up with r by gamma minus 1. These are very important relations of thermodynamics which you need to recall, and you need to remember them as well. Let us go to the first law of thermodynamics. A quick recapitulation, we had discussed it earlier also when we discussed about deriving the energy equation, but we are revisiting it once more quickly. So, this is the statement, you have del q plus del w equal to d E. The first law of thermodynamics is being written for a closed system here for simplicity, and in this equation E is a state variable and hence it happens to be an exact differential. So, its value depends only on the initial and final states of the system. That is basically a characteristic of a state variable. It depends only on initial and final states when you talk about its change, and that is why it is not dependent on the path that you follow between the initial and final states. That means, what kind of process has taken it from the initial to the final state does not matter really, whereas the inexact differentials del q and del w are process or path dependent. So, for a given differential change in internal energy, there are an infinite number of different processes or paths that one can follow, by which heat can be added and work can be done on the system to bring about that change in internal energy. And what are those different processes? These are three possible main types that we have stated here. One is an adiabatic process where no heat is added to or taken away from the system in the process, and therefore, del q is going to be 0. This is a very important process. Then we talk about a reversible process. When does that happen? When no dissipative phenomena occur in such a process, which can lead to irreversible effects. That means, you cannot take the system back to its original state under any circumstances, because it is an irreversible effect which has occurred. That happens in the case of effect of viscosity, thermal conductivity and mass diffusion, but here they are absent because there are no dissipative phenomena which can cause the irreversible effects. So, these effects of viscosity, thermal conductivity and mass diffusion, if they are absent completely from the process, then there can be no irreversible effects, there can be no dissipation, and therefore, it is termed as a reversible process. So, when you have an adiabatic process where there is no heat transfer and the process is also reversible, then what we have is the isentropic process. So, effectively the third process is basically a combination of the first and the second. So, for a reversible process, we can show that the dW, the work done at the system boundary, can be expressed as the product of minus P times dV. dV is the incremental change in specific volume of the system due to a displacement of the boundary of the system. So, if you plug in these details into the first law equation, then del q is 0 and then del w is minus P dV, that gives you dE, the change in internal energy. So, this is broadly a very basic exposure to first law of thermodynamics. Let us look at second law of thermodynamics briefly. So, the equation that we have over here is expressing the change in entropy, which is also an exact differential, and therefore, it is a state variable. So, the ds is represented as the ratio of del q by t. So, once again del q is process or path dependent divided by T, the temperature at which the heat transfer occurs, and then we have added a term ds with a suffix irrev, which stands for irreversible. So, that is a change in entropy which is associated with the irreversibilities. So, what does this equation state? That it states that the change in entropy during an incremental process is equal to the actual heat added divided by the temperature plus a contribution from the irreversible dissipative phenomena of viscosity, thermal conductivity and mass diffusion occurring within the system. So, here we are talking about a possible presence of those irreversibilities. Remember that when we were discussing about a completely reversible process, then we said that these irreversibilities cannot exist in such a process. However, here we are keeping the possibility alive. So, these dissipative phenomena will always increase the entropy, and hence the ds irreversible is always greater than equal to 0, it can never be less than 0. However, for a reversible process, that part of the entropy change will go to 0. So, in general, we can reduce this statement to a form like this, that ds is greater than equal to del q by T, and of course, that basically means that without explicitly mentioning ds irreversible, you have just changed it into an inequality. For an adiabatic process, since del q will be 0, it basically reduces to ds greater than equal to 0. That means, even though there is no heat transfer, due to irreversibilities within the system, the entropy will be greater than equal to 0. So, the process will proceed in general in a direction such that the entropy of the system plus surroundings always increases or at best stays the same. So, when it stays the same, we are talking about the equality, otherwise it becomes greater than 0. When we put in the expression for the del q reversible, then it is T ds minus P dV, that is the reversible work that we were talking about, is equal to dE. That means, basically we have written the first law, only thing is we have replaced the del q expression by T ds, which happens to be the del q for a reversible heat transfer, and this is of course reversible work done on the system. So, this is a possible expression of first law, where we are putting in the ingredients of the second law. It can be alternatively expressed like this by transposing this term to the right hand side. Another possible expression for the T ds in terms of enthalpy would be dH minus V dP. How do we get it? We can go back to the definition of enthalpy, specific enthalpy precisely, and then you try to take a differential of the specific enthalpy, and you try to take the differential of the right hand side terms and try to show that you can also write this possible form of the first law. When you integrate this expression, then what do you get? You can get two outcomes. One is this, another is this. If you are talking about a calorically perfect gas, so you get the entropy change between the end state 2 and the starting state 1, that gives you S2 minus S1 in terms of the temperature ratio and pressure ratio, or temperature ratio and specific volume ratio. So, these equations can be obtained by using these two possible forms of the first law and integrating them. when Cp and Cv are constant, the integration is simple enough. That is why you have these forms only for calorically perfect gas. If it is a thermally perfect gas, then the integration is not all that straightforward, because Cp will then become a function of temperature, for example, and therefore, you have to evaluate this integral. Similarly, the same thing will happen when it comes to Cv. So, when you look at isentropic case, then you set ds equal to 0, and then from those two equations you are able to get this form. From there, with this expression, you are able to obtain a relation between pressure ratio and temperature ratio, and from the other expression you are able to get this, and on solving that you get this, an equation between the specific volume ratio and temperature ratio. So, when you put everything together, you now have an equation for calorically perfect gas. This gives you the isentropic equations. So, the connection between pressure ratio, density ratio and temperature ratio, this is a very, very important relation. So, in all isentropic processes involving calorically perfect gas, we have to invoke these relations on a routine basis. So, that was a very preliminary revision of the laws of thermodynamics and concepts of perfect gas, equation of state, thermally perfect, calorically perfect gases, etc. Now, let us look at a very, very important concept, that of speed of sound in a compressible medium. And additionally, when we deal with it, we also come up with the definition of Mach number. So, here we are talking about propagation of sound through a medium. So, sound is a weak pressure wave. So, when a small sound is created by a sound source, what happens is the acoustic energy that is liberated into the medium, that creates additional collisions with the surrounding molecules and atoms of the gas, and the collisions propagate the energy into the medium further and further. But because a low amount of energy is propagating through the medium, only differential changes are created in the properties of the medium. So, that wave is a weak pressure wave which is propagating through the medium with a speed of a, let us say. And then if you are riding the sound wave, what do you see? You see that the air is moving towards you at the speed of a, because that is a relative scenario. And if you look at the density of the medium, for example, you will see it is rho, if the pressure it is P, etc. And when you look behind, you will see that very small changes have happened to the speed, to the density, to the pressure, to temperature, etc. When this is a stronger wave than a sound wave, then these changes could become large. Now, this is basically a one dimensional flow problem. You do not see changes in properties along y or z, etc. You can only see changes along this direction, which we can call as the x direction. So, when you look at the continuity equation in one dimensional steady flow, it happens to be a form like this, rho 1 u 1 equal to rho 2 u 2. If you were looking at the continuity equation as applied to a control volume like this, along which the flow is just happening in one dimension. There is no variation in the area across which the flow is taking place, and if I call this as station 1 and this other one as station 2, the flow enters the control volume through station 1 and leaves the control volume through station 2. You can look at it that way. So, it effectively boils down to the equation rho 1 u 1 equal to rho 2 u 2. So, you can imagine a similar control volume here surrounding the sound wave. What enters is 1, what leaves is 2. Using that principle, we have written down this equation rho into A, because A is the velocity which is coming in from the station 1, and then there is a slight change in rho and slight change in A. With that you get this expression, but we are ignoring the product of differentials because they are very small quantities. So, finally, if you rearrange these terms, what do you get? You get an expression for the speed of sound A minus rho dA d rho. Now, if we were to apply the momentum equation in the one dimensional steady inviscid flow devoid of body forces, then what expression would you get? You will get an expression like this: P 1 plus rho 1 u 1 square equal to P 2 plus rho 2 u 2 square. So, you can go back to your lectures on conservation laws, and there you have the different integral and differential forms. You can pick up the integral form and try to integrate the momentum equation in 1D steady inviscid flow devoid of body forces, let us say along the x direction. If you do that, you will come up with an equation like this. So, we are using that equation here. When you work out that equation, it gives you an expression for dA. You plug that into the previous expression where dA appears here in the numerator, and now you have an expression for A by combining these two equations together, from where you finally get an expression for A square, which gives you dP by d rho. Now, how does the change in pressure and density take place over here? They were very small changes. These changes occurred within the sound wave and they were very small, the flow gradients were very small, and therefore, the irreversibilities or the dissipative effects of friction or thermal conduction or mass diffusion, etc., would not occur here. Neither is there any question of any heat addition or subtraction. Hence, the process through which all this has happened is adiabatic and reversible, therefore isentropic. So, when we write this equation, we additionally associate the subscript s and make it as a partial derivative, saying that this A square is defined under isentropic conditions. So, the above equation shows that the speed of sound is a direct measure of the compressibility of the gas. Let us elaborate on this concept. So, we have written this. We are talking about pressure change and density change being linked with each other. Remember that density is inverse of specific volume. If you take a differential, you will get this. When you plug that into this equation, you will get this form, and there comes your specific there comes your partial derivative of V with respect to P. That means change in volume with respect to change in pressure, and we are talking about compressibility here basically. So, when you plug all these equations together, what do you get? You get an expression for A in terms of the compressibility. What compressibility are we talking about? We are talking about isentropic compressibility. So, A is under root V by tau s. It is clear from the expression that if tau s tends to 0, that means it is an incompressible flow, then the sonic speed will tend to infinity, because it will be under root V by 0, which will give you the infinite form. Now, if you plug in the isentropic equations for calorically perfect gas, you invoke these relations, and you can use this as a combination of these two portions. So, that is P v to the power of gamma equal to constant. How does it help? It helps us to evaluate the expression for del p del rho for isentropic case to be gamma p by rho. Once you substitute that into the equation for A, you have under root gamma p by rho for A, and then if you bring in the equation of state, perfect gas equation of state, you get it as root over gamma R T. So, you have now got alternative definitions for speed of sound. Further, we are interested to bring in the Mach number now, which is nothing but the ratio of the flow velocity with respect to the speed of sound. That is the Mach number. So, when the flow velocity is traveling at a speed lower than that of the speed of sound, we talk about a Mach number less than 1, which is called as a subsonic speed. Why subsonic? Because we are comparing it with the speed of sound and it is lower than that. When it is exactly equal to 1, it is sonic. When it is greater than 1, it is supersonic. That means V has exceeded the value of A. Now, interestingly, the square of the Mach number can be shown to be proportional to the ratio of kinetic to internal energy of the gas. So, the kinetic energy is due to the directed motion of the gas, and it is being compared with the random thermal motion of the molecules, which is visible at the microscopic levels. So, when you take the ratio and you just take it through a few rounds of conversion by substituting E equal to CVT, which is true for calorically perfect gas, and then RT by gamma minus 1 and so on, you will be able to show it as gamma into gamma minus 1 by 2 m square. That means, the ratio of kinetic energy to internal energy is proportional to m square. So, what did we learn in this lecture? We briefly recapitulated the basics of thermodynamics. We developed the isentropic relations for a calorically perfect gas, and further we discussed about propagation of sound wave through a medium, and we derived an expression for sound wave, and subsequently we brought in the definition of Mach number. So, with this we end this lecture. Thank you.